Welcome to MiniWeb Tool. All right, let's kick things off with a little mathematical puzzle that seems to break all the rules. Take a look at this. 7 times 4 equals 34. Now I know what you're thinking. That's just wrong, right? It looks like a typo, a huge mistake. But what if I told you that this equation is 100% correct? It's not a trick. It's just written in a different numerical language. This is the language of Octal, a base 8 system that's actually super important for how computers work. So, over the next few minutes, we're going to break down exactly what that means. We'll start with that curious calculation and talk about why your brain kind of fights you on this. We'll learn how to think in powers of 8, see why it sits a critical bridge for computer code, and finally, I'll show you a much smarter way to handle these problems. Okay, let's dive in. So that feeling you get, that little voice in your head saying, that's just wrong, it's not you, I promise. It's actually a feature of how your brain has been trained to think its entire life. See, your brain is an absolute master of one particular system, our everyday decimal or base 10 system. You know, we've got 10 fingers, so our whole world of numbers is built around the number 10. You've been practicing it your entire life, which makes you incredibly fast, but it also gives you a really strong bias. And here's where the confusion really kicks in. It's all about how different systems use the same symbols. In our normal decimal system, we count up to 9, and then the next number is 10, which means 10. Simple. But in Octal, you only use the digits 0 through 7. That's it. So when you get to 7 and add 1, the next number is also written as 10. But here, 10 actually means 8. Same symbol, totally different value. And this is why it feels so weird at first. Your brain is just hardwired for base 10. Then you have to get used to the fact that the digits 8 and 9 just don't exist. Counting goes 6, 7, and then boom, you're at 10. It feels completely unnatural. And even basic stuff like carrying the 1 works differently, making bigger calculations a real headache. So how do we get around this? Well, we kind of have to rewire our thinking. And to do that, we need to go back to something we all learned but probably don't think about much: place value. Let's do a super quick refresh on our familiar base 10 system. When we see the number 345, we instantly know what it means. But why? Well, it's because of place value, right? The 5 is in the ones place, the 4 is in the tens place, and the 3 is in the hundreds place. Each spot is just a power of 10. Now here's the really cool part. We can take that exact same logic and just apply it to Octal. The only thing we change is the base number. Instead of powers of 10, we're going to use powers of 8. So if we have the Octal number 345, the 5 is still in the ones place, but the 4 is now in the 8's place, and the 3 is in the 64's place. And when you do the math, 3 times 64 plus 4 times 8 plus 5 times 1, you get 229. And just like that, you see how the octal number 345 is the same as 229 in our regular decimal system. It's just simple multiplication once you get the place values. Okay, but what about going the other way, from our system back to Octal? It's just a simple process of repeated division. You take your number, 229, and divide by 8. You get 28 with a remainder of 5. Cool. Now take that 28 divided by 8 again. You get 3 with a remainder of 4. Do it one more time. 3 divided by 8 is 0 with a remainder of 3. Then you just read those remainders from the bottom up, and there's your number. 3, 4, 5. Okay, so we've got the how down, but what about the why? Why does this system even matter? Well, this is where we get to the real aha moment and see Octal's true purpose. So computers don't think in base 10, they think in binary, base 2. Everything is just a 1 or a 0. But for us humans, trying to read a long string of binary code like this is, well, it's a nightmare. It's just a clunky, error-prone wall of ones and zeros. But here's where Octal becomes this kind of magic translator. Because 8 is a power of 2, it's 2 to the power of 3, it means that every single octal digit maps perfectly to exactly 3 binary digits. It's this beautiful, clean, one-to-one relationship. So that big, messy string of ones and zeros we saw before, you can just break it up into groups of 3, and suddenly it becomes the much cleaner, much simpler octal number 651. This is used all the time in the real world, like with server commands. When you see something like chmod 755, those numbers are actually octal digits being used as a shortcut for complex binary permissions. Alright, so now we have everything we need to finally crack our original puzzle. To solve 7 times 4 in Octal, we first do the math in the system we know best, 7 times 4 is 28 in decimal. Then we just convert that result, 28, back to octal. Divide 28 by 8, that's 3 with a remainder of 4. Divide 3 by 8, that's 0 with a remainder of 3. And you read those remainders from the bottom up, and what do you get? 34. And there it is, the puzzle is solved. But you can probably see how doing this for every little calculation would get old really fast. It's fantastic for understanding the logic, but it's not exactly practical when you need a correct answer quickly. I mean, just look at this. Imagine trying to subtract these two octal numbers by hand. The rules for borrowing are different, a standard calculator won't help you, and one tiny mistake messes up the whole thing. And look, doing it by hand is a great mental workout, but in any real-world situation, whether you're a student trying to check your homework or a programmer debugging code, you need accuracy and speed. There's just a smarter way to go about it. This is where something like a dedicated tool, an octal calculator, is so incredibly helpful. It's not just about getting instant answers, it's about avoiding all those little manual errors that are so easy to make. It's perfect for checking your work and making sure you're on the right track. And honestly, the best part for anyone trying to learn this stuff is that the good tools don't just spit out a number. They show you their work. They walk you through the entire process, the conversion to decimal, the calculation, and the conversion back, which actually helps you learn it even better. All right, let's quickly recap what we've covered. Octal is a base 8 system using digits 0 through 7. Its real superpower is being a human-friendly shortcut for long, messy binary code. That's why it's still super important for things like file permissions. And while understanding how to convert the numbers is key, using the right tools can help you learn and get things done instantly. So the mystery is officially solved. 7 times 4 equals 34 isn't a weird mistake. It's a perfectly logical fact in a different system. And now you have the knowledge to understand it and the tools to solve any octal problem that comes your way. Pretty cool, right? To continue learning about useful tools and concepts just like this one, make sure to subscribe to MiniWebTool. Thanks for watching.